Welcome to The Explainer. Today, we're going to dive into a fundamental principle of physics that, believe it or not, powers everything from diesel engines to your refrigerator. And it's all based on the simple act of squeezing. All right, so let's kick things off with a little puzzle, one that kind of seems impossible. Imagine you've got a cylinder, and at the very bottom, there's a little piece of dry paper. How on earth could you set that paper on fire using nothing but the air inside? No matches, no lighter, nothing. Well, the answer is actually pretty simple, but it's incredibly powerful. If you just slam a piston down with extreme speed, compressing that air, you can generate enough heat to make that paper burst into flames. And this isn't some kind of magic trick. It's a real-world demonstration of a physical principle called adiabatic compression, and it is at work all around us. Okay, so to really get how slamming a piston can literally create fire, we've got to dig into the core concept here. It all comes down to one really important rule in thermodynamics. So this whole process has a name. It's called adiabatic, and that comes from this Greek word, adiabatos, which basically means impassable. And that's the key idea. Imagine heat is trapped. It's on lockdown. It can't pass into our little system from the outside, and it can't escape from the inside either. Now, what's super interesting is that you can get to this impassable state in one of two ways. First, you could have perfect insulation, right? Like a flawless thermos that lets zero heat in or out. But the second way is way more common. You just do it really, really fast. In our fire piston example, the compression happens so quickly that the heat it creates literally doesn't have a chance to snake out through the cylinder walls. Okay, so if all that heat is trapped, right, it can't go anywhere, what happens when you do all that work on the gas by squeezing it? Where does all that energy actually go? Well, the answer is hiding in plain sight, right in the first law of thermodynamics. You can think of it as like the universe's most basic rule for energy bookkeeping. It just says that the change in a system's internal energy is simply the heat you add to it plus the work you do on it. And this is where the magic happens. Remember, in an adiabatic process, no heat gets in or out. So that Q term, the heat, it's zero. That means every single ounce of energy you put in by doing that work, by jamming that piston down, it has nowhere else to go. It gets dumped directly into the system's internal energy. So what is internal energy anyway? Well, you can just think of it as how fast the little molecules of gas are zipping around. When you do work on the gas by squeezing it, you're basically force-feeding those molecules a shot of pure energy, and they just start ricocheting off the walls like crazy. And for us, we feel that frantic movement as an intense, super fast rise in temperature. And you can see this perfectly on a pressure-volume graph. That black line representing the adiabatic process is way steeper than the others. That shows you that for the same change in volume, you get this massive spike in both pressure and temperature. And why? Because all that energy from your work is trapped inside, just supercharging the gas. All right, let's switch gears a bit, because this one simple principle, it's a two-way street. You can use it to create crazy heat, and you can use it to create extreme cold. It's really versatile. Let's talk about heat first. The perfect example? A diesel engine. You ever wonder why diesel engines don't have spark plugs like a regular car? This is why. They literally make their own fire. So inside a typical diesel engine, that piston slams down and squeezes the air and fuel mixture down to just 1/20th of its original size. I mean, that is an incredible squeeze. And because this happens so fast, it's basically an adiabatic process, the temperature just skyrockets. We're talking from room temperature to over 700 degrees Celsius, almost instantly. It gets so hot the fuel just bursts into flame on its own, no spark needed. Okay, but what happens if we flip the script? The physics here is it's beautifully symmetrical. If squeezing a gas really fast makes it hot, what do you think happens when you let it expand really fast? You guessed it gets cold. This idea, adiabatic expansion, is the secret sauce in every single refrigerator and air conditioner. First, a compressor squeezes a refrigerant gas, making it hot. Then, that hot gas flows through coils on the back and releases its heat into your kitchen. After that, it's allowed to rapidly expand, which makes its temperature plummet. And that now frigid gas is what circulates inside, soaking up heat and keeping your food cold. You know, this isn't just about engines and refrigerators. The effects of adiabatic heating and cooling are happening all around us, all the time, shaping the natural world in ways you probably never even thought about. Take clouds, for example. Moist air rises, the pressure drops, so it expands adiabatically, it cools down, and poof, the water vapor turns into a cloud. Even the sound of my voice reaching you right now, that's just a series of super fast adiabatic compressions and expansions of air. It's happening deep in the Earth's mantle and even at the cutting edge of quantum computing. All right, so we've covered a lot of ground. What's the one big takeaway here? What's the main thing you should remember from all of this? It all boils down to this. It's super simple, but it's so powerful. A fast squeeze makes a gas hot. A fast expansion makes a gas cold. That's it. See, this isn't just some boring topic you find in a physics textbook. It's a fundamental engine that drives both our technology and the natural world, from the roar of a diesel truck to the quiet clouds forming overhead, all of it powered by a simple change in pressure. So, my question to you is, now that you know what to look for, what in your world runs on this hidden principle?